Hello everyone, I welcome you all to this video series on failure theories. We are gradually trying to build different failure theories and we are trying to wrap our mind around the basic rudimentary concepts that are required to build the failure theories. So today we are going to find the normal stress and tangential stress acting on an inclined plane. That you could see that the inclined plane AC, that you could see that there. And we are going to find what is the normal stress on this inclined plane AC and also the tangential stress on this inclined plane. Now in the previous video, we were able to do just that, but this physical scenario is a little bit more involved. You could see that there is a rectangular member with a thickness T and it is subjected to a normal stress sigma 1 on the horizontal direction, and it is subjected to the sigma 2, the vertical normal stress sigma 2, right? And besides that, this rectangular member is also subjected to shear stresses. You could see that the shear stress tau, that you could see that, okay, denoted by the green color there, it is also subjected to the shear stresses. Now you could see that the shear stress that is acting at the top, maybe I could highlight that. I'm talking about this particular shear stress. If you consider that to be the action, then to maintain equilibrium, there is going to be a reaction that you could see here at the bottom. Okay, so one is the action, the other one can be considered to be the reaction to that action. And you could see that these two are equal forces but opposite in direction and separated by some distance, so that should constitute a couple, and this couple should rotate the entire rectangular member in the anti-clockwise direction. But we are dealing with structures, nothing should move and nothing should rotate. So in order to make sure that this structure has a degrees of freedom 0, what I mean by that is the structure should not actually move. So there is a restoring couple that is going in this direction, that you could see that here. So one action couple that is acting in the anti-clockwise direction, and there is a restoring couple. And the restoring couple manifests because of the two complementary shear stresses, okay, acting on the left side. Let me zoom that up a little bit, that you could see that. And also on the right side, that you could see that these two are complementary shear stresses. Okay, fine. Now let us try to find the expression and let us try to build the mathematics. Fine. Now the first step is to define the load that is going in the vertically downward direction. Okay. So I'm interested in finding what is the load that is going in the vertically downward direction. What I mean by that is I'm interested in the shear load. So this is the load that I'm interested in. So let me highlight that. Maybe I can use green color. So this is the load that I am interested in. It is the shear load that is going in the vertically downward direction. Okay. Now, how do you find the load? That's very simple. Stress is load by area. So load should be equal to stress into area. So load P1, this is the load. P1 is equal to stress, which is tau, okay, into the area over which the load is distributed, over which the stress is distributed, okay. So the stress is distributed over the cross-sectional area, which is the height. Here is the height, it is AB, and the thickness, okay? So that's what is written here, it is AB into thickness. And the load is acting in the downward direction. We can assume this to be a uniformly distributed shear load, okay? So the load is just uniformly distributed, okay? So we got the expression for the load. In exactly the same manner, you can find what is the load that is acting on this green box. Okay, so that is the green box. So how do you find that? In exactly the same manner, stress is load by area. So load P2 should be equal to stress into the area over which the stress is distributed. So stress is tau and the area is this length. I mean, what is that length that I'm talking about? I'm talking about this length, and that length is same as BC. Okay. that you could see this length BC and the top length, the rectangular box length, over which the stress is distributed. Okay, I'm interested in that particular load alone. I'm not interested in I'm not interested in the total load, but I'm just interested in the tangential load that is distributed in the rectangular box. Okay, fine, for a specific reason, because that is the load that will be transmitted to the inclined plane. So that's the reason why I'm interested in that specific load. So that is given by the expression stress into the area over which it is distributed, which is the length into thickness, BC into thickness. Okay, got it, fine. Now look at this load, P1. This load I'm talking about, this particular load, okay, that according to, that it is going in the downward direction, but that load that is going in the downward direction like this is transmitted to each and every plane in the downward direction. So it goes here, it goes here, and it goes here. It also goes to the inclined plane. Okay, so there you could see that the load is going in the downward direction. So that load P1, it is acting on the inclined plane just like this. Okay, that is P1. And you could see that this load P1 can be resolved into two components. One is the component that is tangential to the inclined plane, that is this particular component, and the component that is perpendicular to the inclined plane, it is this particular component. And the component that is tangential to the inclined plane is P1 cos theta, right? And the component that is perpendicular to the inclined plane, it is P1 sin theta. Once you have computed the tangential load and the normal load, then the process is now easy. You can just define what is the normal stress that is acting on the inclined plane, which is the load, which is P1 sin theta, here you go, divided by the area. So that is the normal stress. So this load, what is that load that I'm talking about? I'm talking about this specific load, this load, okay, that I'm highlighting. P1 sin theta is actually compressing the inclined plane. So since it is compressing, I'm assuming a negative sign to that. Okay, and by convention, I will assume a positive sign for the tangential load acting in this direction. It is positive. The tangential load that is going in this direction, it is negative. So obviously, we're going to get a negative sign here. Okay, so the normal stress is the normal load P1 sin theta divided by the area of the inclined plane, which is AC into thickness. So that's what we have written here, that you could see P1 sin theta, the normal load, divided by AC into thickness. We already got an expression for P1. All you have to do is take that expression and plug it here. Mathematics is just like moving objects. All you have to do is take this expression for P1 and just plug it here. All right, so here we got the expression for P1 that is substituted. It is tau into AB into thickness into sin theta, divided by the denominator is as it is. The thickness in the numerator and the denominator, they cancel each other out. And AB by AC, if you look at this triangle, what is AB by AC? It is cos theta. It is adjacent side divided by the hypotenuse side. That is cos theta. Of course, this is opposite side. Okay. So AB by AC is adjacent by hypotenuse. So that gives us cos theta. So when you substitute, it becomes minus tau into sin theta cos theta. So that is the expression for the normal load that is acting on the inclined plane, AC, due to P1. Got it? Fine. Next, what is the expression for the tangential load that is acting on the inclined plane due to P1? The tangential load that is acting on the inclined plane due to P1. So we are going to find that. So here we go. So what is the tangential load? The tangential load is P1 cos theta. So there you go. Yes, P1 cos theta. You can see that this is the tangential load, P1 cos theta. Tangential load divided by the area over which the tangential load is distributed. It is distributed over this inclined plane tangentially. So it's going to be the inclined area, which is AC into thickness. Got it? So load is P1 cos theta divided by AC into thickness. So that is the tangential load. So here we go. That is P1 cos theta divided by AC into thickness. Okay. So substitute the value for P1. You could see that the value for P1 is substituted here. It is tau into AB. And you simplify the mathematics. And AB by AC is cos theta, as we discussed earlier. So you get tau into cos square theta. So that is the expression for the tangential load that is acting on the inclined plane. Okay, acting on the inclined plane due to P1. Okay. Now we are going to do exactly the same, but for P2. The normal load that is acting on the inclined plane due to P2 and the tangential load that is acting on the inclined plane due to P2. What is P2? So here we go. So if you want, I can do this one more time. So here is our triangle. This is A, this is B, this is C. And let me represent the tangential load. Okay, let me represent the load that is transmitted. And the load that is transmitted is in this direction. Okay. Now, how do I say that? You have to go back to this original diagram. So let me go back to the original diagram. I'm interested in the load that is distributed in this rectangle. Okay. So I'm interested in this region. So that load is given by the expression stress is load by area. So load is stress tau. Here we go. Into area, which is the length is BC. This length, it is BC into thickness. Got it? Okay. Hope you're all following. Fine. Tau into BC into thickness. So that's the load, and it is transmitted to each and every plane beneath it. That load is transmitted. So this plane is subjected to this same load, P2. Okay? It's transmitted to each and every layer beneath it. That P2. Okay, so that P2 is transmitted to each and every layer beneath it. So all the layers are subjected to P2. I'm not representing that, just to make sure that the diagram doesn't look so cluttered. So this is going to be your 90 minus theta. So, okay, it is 90 minus theta. You can resolve this force into two components. One is the tangential one, which is P2 cos 90 minus theta. That is obviously P2 sin theta. And we know that the load that is going in this direction by convention, I'm putting a negative sign there. And the load that is vertical component, that is P2 sin 90 minus theta, which is cos theta. Of course, it's compressing, so I'm putting a negative sign there by convention. Yeah. So now I know what is the expression for the normal stress and the tangential stress due to P2. Okay, it's the same. So the normal stress is the normal load, which is P2 cos theta, divided by the inclined area, which is AC into thickness. So that's what I have written here. So that's right. So the normal load is P2 cos theta divided by AC into thickness. Right? Fine. Of course, I have to put a negative sign. So substituting the value for P2, which is tau into BC into thickness into cos theta divided by the inclined area, which is AC into thickness. So mathematics, you just cancel the thickness on both sides. And BC by AC, it is opposite by hypotenuse, that is sin theta. Substituting, you get the expression for the normal stresses minus tau into sin theta cos theta. Got it? In exactly the same manner, find the expression for the tangential load, which is the tangential stress on the inclined plane, which is the tangential load, which is P2 sin theta, of course, negative sign divided by the inclined area. So substitute the value for P2 to do the mathematics. BC divided by AC is sin theta, opposite by hypotenuse. So sin theta into sin theta is sin square theta. I got the expression for the tangential load that is acting on the inclined plane. So what we have done so far, we have got the expression for the normal load acting on the inclined plane due to P1 and also due to P2, and the tangential load that is acting on the inclined plane due to P1 and also due to P2. Well, we computed separately. So two normal loads, one for P1, another one for P2. So we have to add them. And two tangential loads, one for P1, another one for P2. And we have to add them to find the total net normal load. Right? Here is the expression for the net normal load. So there you go. You just add the two. Okay? So this is what you will be getting if you add minus tau sine theta cos theta minus tau sine theta cos theta due to P1 and P2. So 2 sine theta cos theta can be written as sine 2 theta. So that is it. So let me highlight that. So this is the expression for the net normal load. And the expression for the net tangential load is, of course, due to P1 and also due to P2. So these two terms. So you can pull tau outside, and cos square theta minus sine square theta can be written as cos 2 theta. So this one. Okay. Now, what is this? So this is the expression for the, so this is what we considered. We considered an inclined plane. Well, we didn't consider an inclined plane that way. We considered an inclined plane in this fashion. Okay. This is our inclined plane AC. And we computed the normal stress and the tangential stress on this inclined plane due to shear stress. Okay. But remember, it is not only shear stress, but it is also subjected to sigma 1 and sigma 2. And what about the normal stress and tangential stress due to sigma 1 and sigma 2 on this inclined plane? That we computed in part 2 of the video. Okay, so I'm going to add those results to the results what we have got today. Okay, so the results for the normal stress acting on the inclined plane due to sigma 1, sigma 2 should be added to this result. And the result for the tangential stress acting on the inclined plane due to sigma 1 and sigma 2 should be added to this particular result. So that's what I have done here. So there you can see this is the final expression. Okay, this is the final expression for the normal stress. So this is this box that you see here. Maybe I can highlight it so a little bit strongly. Yes, even strongly. Here we go. This is the expression for, yes, the normal stress acting on the inclined plane AC due to sigma 1 and sigma 2. And this one, slightly different color, maybe blue. Yeah, this is the expression for the normal stress acting on the inclined plane due to the shear component tau. And this is the expression for the tangential stress that is acting on the inclined plane due to sigma 1 and sigma 2. And this is the expression for the tangential stress that is acting on the inclined plane due to the shear stress. Okay, shear stress tau. So the one that I have highlighted in blue we derived today, and the one that is highlighted in yellow we derived in part 2 of the video. Okay, fine. So what do we do with this expression? So now this enables us to give the expression enables, okay, fine. We are able to find what is the normal stress acting on the inclined plane and also the tangential stress that is acting on the inclined plane. So what do you do with this? Well, now what we can do is we can find what is the expression for the maximum normal stress that is acting on the inclined plane. And also we can find the expression for the maximum tangential stress acting on an inclined plane. So we are just going to do that, find the expression for the maximum normal stress. Okay, so there is a plane that will carry the maximum normal stress, and there is going to be a plane that is going to carry the maximum shear stress. Which plane? It's an inclined plane, but it may be an inclined plane, maybe not. But what plane? So we have to locate that plane. So we are also going to find the plane, locate the plane that will carry the maximum normal stress and the plane that carries the maximum shear stress. We are going to do that in the next part of the video. So enough for today. So thank you all for your patience. Thank you so much.